When we think about the topic of recovery, most of the time we just go towards the default of the different recovery strategies and the different types of recovery that you can do. Although these different strategies do assist with the athlete's recovery from sessions, we do need to understand the fundamentals of recovery. And in this case, understanding the fundamentals of fatigue and recovery are important. This video will discuss the importance of getting the optimal balance between training and recovery correct. The first part will focus on setting the scene, focusing on the physiology of training overload and adaptation, key principles of the training process. Part 2 will cover the overtraining syndrome, the continuum from optimal training to fatigue and overtraining. And in the third and final installment in this introductory video to recovery, it will focus on preventing excessive fatigue and overtraining. Through optimizing the balance between training and recovery, we can better provide the correct platform performance and adaptation whilst minimizing potential negative effects from ineffective recovery. Early on, exercise training used to improve physical performance was based on intuition and folklore. Several coaches often had a feel for the sport. They were able to manipulate training loads to induce changes, which were accompanied by an improvement in the athlete's performance. However, in the early 1900s, physiologists started applying their skills to study the physiology and biochemistry associated with exercise and adaptations to exercise training. Gradually, the knowledge base increased, explaining the mechanisms behind muscle contraction, breakdown, and regeneration fatigue and motor coordination. As this knowledge became more accessible, it started to be applied in various aspects of society. For instance, the well-being of miners increased once their heat tolerance was understood. And astronauts learned the necessity of simulating weight-bearing activities in space to prevent muscle and bone loss. It was only in the late 1970s that sport physiology was applied to sport training, with the goal of improving performance. This launched the concept of a scientific approach to training. As the scientific approach became more mainstream, coaches started to realize the importance of understanding and applying the principles of biology, particularly the principle of dose and response, i.e., the dose of exercise is the stimulus of a training session, and the response is the outcome from that training session. It became clear that athletes whose coaches understood and applied these principles had an advantage over their competitors. The scientific approach to training initiated the principles such as interval training, circuit training, endurance training, and the periodization of training. Other strategies to improve performance, such as the application of principles of nutrition, biomechanics, and psychology, also started to influence preparation for peak performances. Perhaps the most important principle of biology that has applications for training and athletic performance is that of overload. This principle was first studied systematically more than 50 years ago. Knowledge of this principle has continued to grow since then, forming the basis of all training programs. A more precise application of the principle of overload in training programs has coincided with a better understanding of the physiological and molecular mechanisms of adaptation after repeated exposure to a physical stress. Understanding this principle is fundamental for coaches and trainers. In particular, applying it ensures that athletes' peak performances are more likely to coincide with their competitive events. Although it is not necessary for coaches or trainers to have a detailed knowledge of the biological steps associated with overload and adaptations, understanding the broad concepts will certainly help them to do their work in a more evidence-based manner. An acute stimulus of a training session induces physiological stress, disturbing homeostasis in muscle cells. During exercise, acute adjustments such as elevated heart rate and body temperature occur to maintain internal consistency. Post-exercise, these adaptations revert at varied time courses depending on the exercise nature. For instance, heart rate may normalize within minutes, whilst muscle function could take weeks, and muscle fibers months to fully regenerate. The body responds to repetitive physiological stress through adaptations, with long-term training adaptations resulting from the cumulative effects of short-term exercises. These training-induced adaptations vary based on the type of exercise stimulus, impacting morphology, metabolism, and neuromuscular function, enabling better coping with subsequent physiological stress. The mechanisms of adaptation induced by resistance and endurance-based training are distinct, with each mode of exercise either activating or repressing specific subsets of genes and cellular signaling pathways. And how we implement recovery can also affect these adaptations. For example, with resistance training, there is an associated increase in intramuscular temperature, and muscle treated with cryotherapy after every training session does not incur training-induced adaptations at the same rate as muscle that is not cooled after each session. The physical side of training is interpreted as a stressful stimulus, as described previously. However, non-training stresses such as sleep deprivation, emotional stress, anxiety, and poor health must also be accommodated by homeostatic mechanisms. Athletes often choose to minimize extraneous stress before a competition, tending just to eat, sleep, and train. Regular monitoring of athletes during the different phases of training can track various stresses and identify which athletes are vulnerable to excessive stress or overreaching. Although at the practical level, the training stimulus can be altered by the duration, frequency, and intensity of the training session at the cellular level, the primary stimulus is a combination of the load on the muscle, metabolic stress, and calcium flux. The principle of overload is important for athletic training, with variables such as frequency, duration, and intensity being adjusted to impose the training stimulus. The training frequency describes the number of training sessions in a defined period. For example, at the elite level, training frequency may vary between 5 and 14 sessions per week, depending on the sport and the stage of the training cycle. Duration refers to the time of the exercise session. Athletes competing at the international level usually train about 1,000 hours per year. Exercise intensity defines how difficult an exercise session is. It can be monitored by measuring sub-maximal oxygen consumption, heart rate, blood lactate, the weight lifted during the exercise, or the perception of the effort, RPE. The exercise intensity lies somewhere on a continuum between rest and supramaximal exercise. Rest coincides with basal metabolic rate, whereas supramaximal exercise is defined as short duration, high intensity work done at a load exceeding that associated with maximal oxygen consumption. Athletes should only incorporate high-intensity training into their programs after they have developed a sufficient base. Incorporating too much high-intensity training into the program too soon increases the risk of fatigue associated with overreaching and overtraining. Overload must be carefully applied and increased to improve performance in a systematic way. The concept of varying training volume at various stages of the season is explained by the principle of periodization. If the training stimulus is kept constant, the athlete soon reaches a plateau. Performance levels stagnate, and the athlete may show signs of staleness. This situation can be overcome by applying an overload training stimulus. This altered physiological stress induces further adaptations. The taper involves a reduction in training volume whilst maintaining intensity, and this is essential for peak performance. The goal is to retain the adaptations from training without inducing fatigue. The tapering period should be optimized, as too long can lead to regression in adaptations, affecting performance negatively. A well-implemented taper can enhance performance by up to 6% in trained athletes. Key features of a successful taper include its duration, reduction magnitude in training, and its interaction with preceding training phases. General tapering guidelines suggest a 40 to 60% nonlinear reduction in volume over 2 to 3 weeks, maintaining intensity at a modest reduction in frequency. When the relationship between training and recovery becomes imbalanced, symptoms of fatigue develop, followed by decreased performance. This condition is known as overreaching. Overreaching can be classified as either functional or non-functional, depending on the duration of the decrease in performance and the severity of the symptoms. In functional overreaching, a rebound and improvement in performance occurs after a few days of full recovery. This is known as supercompensation, and it is sometimes used as a strategy to improve performances in anticipation of an important competitive event. The supercompensation principle may be described as a planned breakdown as a result of sustained training, followed by recovery and enhanced performances. Non-functional overreaching is a more severe condition, with decreased performance lasting for weeks or months. The disturbance in homeostasis is reduced after the athlete stops exercising. Various biological systems require different time periods for recovery. This seemingly passive period is important for the subsequent adaptations. Inadequate recovery between training sessions will result in maladaptations, with the accompanying symptoms of fatigue and impaired muscle function. Insufficient recovery prevents athletes from training at the required intensity or completing the required load at the next training session. To enhance the recovery process, athletes often undertake proactive recovery strategies after training, such as massage, cryotherapy, immersion in water of contrasting temperatures, compression, and even stretching. These sessions shift the stress recovery balance in favor of the recovery processes. A purported consequence of this is that athletes can tolerate higher training volumes. The positive effects of the training load may also be enhanced. That covers it for this first section on the physiology of exercise training. Take a short break and see you shortly for part 2, where we will be discussing the overtraining syndrome.